All right, so I just want to do a quick follow-up video for you guys to have a reference. So I'll do this actually in two videos. We'll do one where I do the examples about thermal expansion, and then on the second video I'll do the examples with the calorimetry. Okay, now these will be the same examples that I did in class. Okay, so you can have them for reference, or if you weren't able to be at class for whatever reason, then you've got that for yourself there. Okay. So we talked about thermal expansion in class and how, these train tracks here got all bent up because there wasn't enough gap space available for when they expanded. And so they got too much tension in here, and the tension had to go somewhere. All right. So again, our equation that's of use to us is this guy here. Okay, boom, boom, where alpha is the coefficient of linear expansion. All right, and again, that's a thing that you can just look up, and I'll post a link in eLearn so you can get to those if you wanted to look at them sometime. And then also, I highly recommend that you check out this video here. All right. But what we're talking about is when we have a change of temperature and our bar or whatever the object is either gets longer or gets shorter. Okay. And it's going to get shorter according to that equation where it's the thermal coefficient, expansion coefficient, alpha times the original length, the initial length, Li, and then the temperature change, delta T. Okay. So let's do a quick example on this, so we can see how it works. All right, so suppose that I've got my bike here, and the bike has an original length of 0.8 meters, so 80 centimeters, and it's really cold change, and the temperature drops 40 degrees Fahrenheit, which is about 22 K, and then we would look up. We'd have to know what kind of metal in the bike frame that we're dealing with, but the actual bike is a metal alloy, and so we're going to approximate it as 15 e to the minus 6 inverse Kelvin. Okay, so it's really pretty straightforward in order to work this out. What we're going to do then is we're just going to say that our delta L is alpha Li delta T, okay? And all we have to do is put in our numbers. Okay, so this was 15 e to the minus 6. All right, and I mentioned in class that something we want to start doing now that we've got some experience under our belt is putting our units into our equations. So this is inverse Kelvin. Our length was 0.8 meters. And then our temperature change was minus 22.2 Kelvin. Okay, just like that. So we can come in here and look and see what happens with our units. And I've got 1 over kelvins here, which cancels my kelvins here to leave me with meters, just like that. Okay, so I'm looking for a length. I'm going to get a length out of this. So that's just sort of a nice check. Now, when we put in all of those numbers, we're going to get something that's pretty small. We're going to get here negative 2.66 e to the minus 4 meters. Okay, so if we want to know the actual new length for the part of the bicycle, then we would say L final is L initial plus our delta L. So that's going to be 0.8 plus a negative, which makes it minus. And this is 0.000266. And all those are meters. Okay. So whatever that is. Okay. So it doesn't change by very much. Okay. In fact, you can see that my delta L there is, it's less than a thousandths. Okay. So it doesn't even budge by even half a millimeter on that. Okay. And these thermal expansions they're always like that. Now, what gets tricky with thermal expansion is it is proportional to whatever length you start with. So if I had something very long, like a railroad piece of railroad rail, then my change would be much bigger. Okay, it would be much bigger. Okay, so now what we want to do is take a look at sort of just generally about size. Okay, so like if I have a tabletop, the tabletop has a certain area, and as the temperature in the room changes and the temperature of the tabletop changes, the area of that tabletop is also going to change. All right. And so what we want to do is we want to be able to come up with something that looks like this, but for area. So we want to have area final is area initial plus, let's say, beta area initial delta t. Okay, so it's something that has exactly the same form for us there. Okay, so what we're going to do then is let's start out with area. So A final, and I know my A final is equal to the final length times the final width. Okay, and if I expand on those, what we have for those things, the final length is the initial length plus a change. And same thing with my width, some initial width plus my change in W. Okay, so let's go ahead and do our algebra here. We got 4 terms. We want to distribute like we always do. We've got Li, Wi plus Li delta W plus delta L Wi plus delta L delta W. Okay, so it looks pretty messy. Okay, now we're going to do a little trick here to help it be not quite so messy for us. So I want you to take a look here. I've got this is delta L times delta W. Now in the last example we just saw, we could see that those delta values are very tiny compared to their originals. Okay, so in the example we did, it's less than 1,000 times as small as the original. So here we've got a delta times a delta. So that'd be 1,000 times 1,000, that's 1,000,000. So this delta term on the end there, that is so tiny, okay? And there is no way we could ever measure that thing. So what we're going to do is we're just going to chuck that term, say that is basically 0. It's irrelevant for what we're doing, okay? Now let's look at the Liwi term. That's this guy right here, okay? Well, that's actually the initial area, isn't it? Okay, so we can say here, A final is A initial plus some stuff. So we're going to have Li onto our delta W, which is alpha Wi delta T. And then we've got delta L times Wi, and delta L is going to be alpha Li delta T. And then put our Wi on there just like that, okay? All right, so now this is kind of cool. Check this out. I've got Liwi, which is A sub I. And I've got Liwi, which is A sub I. In fact, those second 2 terms are identical. So I've got 2 of them, really. All right, so let's write it like this. Let's say AF is AI plus 2 alpha AI delta T. Okay, now remember the AI comes from my terms Li and Wi together in both of those things. Okay, but look what's happened here. That's actually what we were looking for, right? Can you see this? Here I was looking for beta. Guess what? There's beta right there. So beta is going to be 2 alpha. All right, now that's good to know. Because you're not often going to find a table of surface area expansion coefficients, but you will find tables of linear expansion coefficients. So what we've got here is we've said that if we need the area expansion, it actually, all we have to do is double the linear one and we'll be good, okay? Now, of course, it's not exact. It's not exact because we ended up having to chuck this term up here. Okay, but how far from exact is it? Well, that was a factor of 1/1,000,000th, okay, or less than 1/1,000,000th, and so it's not off by much. It's pretty darn good. It's going to work for us. Okay, now we could do a similar sort of thing looking at volume. Okay, we could say if we do volume final is volume initial plus, let's call it gamma this time, volume initial delta T, okay, we could go through the same process that we did before. And by that, I mean up here, we did length times width, but what we would end up doing is length times width times height. And so instead of having 2 terms there, we would end up with a third term for the height. All right. And somewhere along the line, we would end up with not just delta deltas there, we'd end up with a delta L, delta W, delta L, delta H, delta W, delta H. All those we'd throw away, and we would also have a delta L, delta H, delta W. That's kind of hard to say. Delta L, delta H, delta W. Okay, and that's really tiny. Now that we're talking about billionths. Okay, and so we definitely want to chuck that. Anyway, when we go through all of that, instead of getting 2A, we would end up getting 3 alpha. Not 2A, 2 alpha. We would end up getting 3 alpha. Okay. So basically we get 1 alpha per dimension. And if we were to suddenly jump into a strange episode of Star Trek or some science fiction thing and be in 4 dimensions, then the expansion coefficient would be 4 alpha. Okay. Assuming that in the 4th dimension, everything works the same way. Anyway, you see what I'm saying there. Okay. All right. So I'm going to end part 1 here. And when I come back, then I'll do the calorimetry examples for you.